Hello viewers, in this class we'll start discussing on the truss member. So for that I have taken an example. In this picture you can see there is a truss having three concentrated loads acting on three different nodes. One end is roller and another one is simply supported, and after the analysis of the truss, the answers have been calculated here. The force in the member AB, which is compression, force in the member BE, which is compression again, force in the member BD and DE. So after the analysis in the STAAD Pro, we have to get the similar result as the output. So now in this the dimensions, if you are observing, the span length is given but the height is not given. Instead they have given the angle between the two members. So out of this we can able to calculate the height of the member. So here we have got an tan theta, let me write here, which is tan theta equal to opposite by adjacent side. This is a trigonometric equation that we all know that. So here theta is 30 degree, right? Adjacent side that goes to A that shows the adjacent side, which is 3 meter. So if I calculate for tan theta, tan 30 degree, it is 0.577, and if I multiply this A to this side, and this will be 1 point, the opposite side is 1.73, right? So the height of member BC, the height of member BC, we can take here, height of member BC is 1.73 meter. At the same time, if you want to calculate it for the member DE, we need to multiply adjacent side as this whole span, since this will be the triangle for that, right? So this is the angle and this is the adjacent side having 6 meter. For that, tan of 30 degree multiplied by 6 meter, so which is the opposite side of the triangle ADE, or we can take DHE, is 3.46 meter, 3.46 meter, which is the height of DE, right? So now we got the geometry of the truss. So by referring to these numbers, we can create a model in the STAAD Pro, and let us analyze for the force in the member. So for that I am going to open this STAAD Pro. I have to take truss. I am naming the file name as truss1, since I have already analyzed a different truss now. So I am choosing the location, and in the desktop I have created a folder named STAAD Pro. I am selecting that, and meter and kilonewton, and finishing off. So now I will close this default grid liner, and will create the model by referring to this coordinate system. So first is 0, since from the 0 I am going to start it now. So if you refer the picture, it is having a 3 meter span, 3 plus 3 6 plus 3 9 plus 3 12, right? In that manner, since it is 3 meter, right? And next coordinate node is at 6 meter, and next node is at 9 meter, and next node is at 12 meter, right? So since it is in isometric view, making it in a front view. So again, this represents the bottom chord of the truss, right? This representing the bottom chord of the truss, and now I am going to make the top chord. So for this top chord, I have to create a point B, D and F. So here for the 3 meter, I do got 1.73 meter height, right? For 3 meter span, I got 1.73 meter height. And again for this one it is 9 meter. For 9 meter, I got 1.73 height. And for 6 meter, I got 3.46. Right. So now this reassembles truss element. So now drawing bottom chord member, connecting node to node and connecting the top chord members. This is the top chord member. So again in this we got connection like this. This is the way, right? So this is the way we got the truss. The similar manner we have got angle between them with the 30 degrees. So now just for the reference, I do take these measurements. Yes, it is 3 meter between the spans, and the height is 1.73 meter height, and here it is 3.46 as we have calculated it earlier. So now we'll go to the general. Since it is a truss, and the steel elements have to assign for this. For that, I am choosing this section database. So in this section database, there are different codes that have been included here. I do take this Indian code, and in the Indian code I do choose this angle. So for the angle, since the choosing of the angle that depends on the span of the element, so in general I do take this 55 by 55 by 10 initially I do take this, and just double clicking on that, and it is over here, and I do assign it to the whole view, because after the analysis during design, the member will be checked for its compression member and tension member later. So before that, for the analysis purpose, I do select this 55 by 55 by 10 mm. So later I have to assign the supports for that. Creating the support. Since one end is pinned here, as you can see in the problem statement, one end is pinned and another end is roller. So for the roller support, I am going to release the Fx and Mz values, and other forces are restrained for the rolling support. So for this, if you want any content how exactly the release are Fx and Mz and other are held together, if you want it, then please comment in the section, then we'll have another video for that. So now I will add this. So I'm going to give the roller support to this one, and hinge support to this one, and roller support to this one. Okay, so after this, now load and load cases. So I'm going to add the different load cases now. So first I will take this dead load case. So in the dead load case, I am going to consider self weight of the structure, and in the live load case, I am going to consider the loads which are acting on the member. So here I will consider this one self weight and close it, and live load. So in the live load, in the truss, since it is a pin jointed, the load is acting on the joint itself. So for that reason, I am going to consider the nodal load. So on this nodal load, I am going to add the Fy load. Since the direction is in a y direction, the force is acting in a vertical direction, so it is y, which has 2.7, 4.5 and 1.8. So 2.7, 7 is a one load and 4.5 is another one. Add it. Next 1.8. So now I am adding this one. Add this and close. This self weight will be there for whole structure. I am assigned to view. So to assign these loads, I have to take this node cursor to select the nodes. So I will select this node and I will select the load. This load is acting on this node as per the problem statement. I am going to assign to that. Again, this load is acting on this node. This is assigned. And this load is acting on this node and this is assigned to that. Okay. So now for the problem statement, we need to take the dimensions of each element, and I will consider the load values which are acting on that. Okay. So now I will take this as a take picture for the report preparation. So after this, the rest thing is to analyze it considering the add option, and then I will run the analysis. So after the run, we should get the 0 errors. We will go to the post processing, apply load. So now here, since it is deflection load is already activated, now I will deactivate that and we will go to the FX. So now FX is the axial forces which are acting in the member. So for that, what I do, I will consider element by element. So now here we got force in the AB 9.45 kilonewton. So this is a member AB. So on this member I am going to check it for separately, since in the whole truss we cannot clearly view it. So for that, taking the new view. So this is the member AB. In this member we got some stresses. Let us see the results. Axial stresses. Now wait. So here you can see 9.454 kilonewton. So which is positive in nature, right? Since it is compression. You can see here the 9.45 kilonewton. It is in a compression. So we got 9.45 kilonewton as a compression for the member AB. Okay, now we got this one. Let us see member BE. This is the member BE, and the member BE got 2.7 kilonewton of compression force, which is this one. So selecting that, taking the new view, and here in this we'll go to the results, view values, beam results, and axial values. So here you can see 2.69 kilonewton, which is a positive value. Again, it is a compression, right? Here 2.7, slightly we can got 2.69, which is near to 2, which is 2.7 itself. Okay, again we got two members verified. Now force in the member BD. In this member we got to check the force, which is 6.75. So now I will choose this BD member, taking to the new view and getting the results for axial 6.75 kilonewton. Again which you can see it is in a positive since it is a compression again. So next member is force in the member DE. This member, in this member the force which we need to get 6.75 in a tension. So I will select that member, taking to the new view and showing the result for axial stresses. In any of the member you can show that the stresses are relating. So here you can see minus 6.747 kilonewtons. So that minus representing the tension and 6.7 kilonewton is the total force which is there in the member. So now we can validate that after the calculation of either method of joint or method of section, we got these forces in the member with the compression and tension. At the same time, the same model is created in the section, and we have observed the similar stresses which is there in the member of the truss. So now I am taking this BD section. I do take the picture of this one which represent the force in the member, and this is the whole member, and in the whole member I do take this one more axial load values, right, and I do take the picture of this too. So after this, the next thing is to prepare the report. So in this report, I am going to take the input as sections and supports and primary load cases. So after that, I do take the pictures of all the three which I have taken during the analysis. So once I selected for all the things in the report, I do take it to the print, and I make it a save in the folder where I have created truss output, and I will save it. So after that, I will go to the respective folder and just open it, and this is the output of the particular truss. And after the analysis of truss, we got these results, and even the method of section and method of joints has given the similar results. So with this this particular truss analysis with using the STAAD Pro is completed. Thank you. If you like this video, please like and subscribe. Thank you.